Start recording. Welcome, everybody. I just copied the interface for the ERC20 token from the Open Zeppelin repos. This, according to the actual ERC, is all you need to be compliant with the ERC20 standard. You'll notice there's no name symbol or decimals. You only need total supply, the balance, transfer, allowance approved, transfer from, and these two events. What I want to try first is I have this token and I want to add the interface to it, maybe to a new one. Then I'm going to deploy both and we're going to check the bytecode. I strongly believe that the bytecode is going to be the same, but how about we just test it? I'm gonna copy the token. I'm gonna make one, let's call it token with interface. We're going to import ERC20.sol. We're gonna say that, let's call it CXX interface is an ERC20, and we probably need a few overrides, right? Override. So this 3 need override, that's good. The events, we can remove them because they are already declared. And all of this, they need an override as well. And that's it. So let's test this. Let's create a new dApp testnet. Good. And we're gonna add a terminal down here. Let's move this up. I'm gonna make this one smaller and this one a little bit bigger. We want to export a couple of variables. So ETH RPC accounts. We want this to be enabled. So Seth will look for our local node for accounts. So if I do Seth, this is a low-level RPC call. If I call Coinbase, it should be the same, right? And now what I want to do is export that as our ETH from. So every call that we do, it's automatically done from this account. And I'm going to dgen token, going to call test, but this is just because it does a build. And I want to see if everything worked correctly. Looks like it did. And we're going to deploy CXX interface and CXX, and we're going to check the difference. So let's do dApp create CXX, and this will already, I believe it will send with enough gas, but we can double check. Okay, so it deployed the token. You can see that this is the token. I'm gonna, this is the code with the constructor, right? So this is what you send to create the token, and the actual runtime code that gets mined. It's a little bit smaller, but should be in there. We're gonna do seth code this. So this is the actual bytecode for the CXX token. Gonna paste this here. And now we're going to create the one with the interface, CXX interface. Okay, it's another one. And we're gonna get its code. And there are better ways to do this, but I'm gonna go the easy route here, and I'm just gonna start going over the bytecode and see if I'm hitting Control D. And as you can see, it all starts exactly the same. And if everything works correctly, all we should see is 32 bytes that are different near the end, and that is the metadata. So let's go over here, Control D, it is exactly the same. And this is exactly the same, the same. And does it change somewhere? Okay, this is the same, and this last part is the same. And we should have 64 selected characters, so that is 32 bytes that are different. This is the metadata that is hashed. So even if you deployed the exact same token, but you change something here, even, you know, a comment, this metadata is going to be different, the hash. So this is good. This is really good because it tells us that having this or having this with the interface is just, you know, the only thing. This is just for the compiler to help us while we're coding, and the bytecode ends up being exactly the same. So I'm going to delete this one, token sol, and I'm going to change this one to be the new token. And it's not going to be interface anymore. This is going to be the good one. And I should probably do the same with this one, just so I can have an easier time later on. I'm gonna have to do the same. If you remember, this other one, the token 2, is the one that had transfer and transfer from be, you know, the repeated code. Instead of token, it had like everything is a transfer from. Transfer is just a special case where, you know, the first parameter is message sender. I think I still like this one better, so maybe this is going to be the actual token, but we'll see. So this is an ERC20 as well. We're going to have to do the same. So public, this 3 are overrides. We remove this event, and all of this are override as well. Good. And test, I'm gonna get the verbosity down to 1 again. All of our tests are working. Good, so that is one less thing. So we added interface, and now we can possibly make our tests a little bit. So we can remove this user2 that we had. And all of this, instead of being like a specific implementation, they can all be ERC20. User 2 can be user, and maybe this and this can be, well, let's just leave them for now, but all of this are just normal users. And where we had, let's see, just doing a little bit of, oh, that's right, because we have mint, which our actual standard doesn't have, but we can just add it because in our case it does, right? So function mint address 2, let's call it like recipient U/56 amount, external. I don't know if we return something or not, but let's leave it at that. And we're gonna need to override different arguments in return statement. Okay, so let's say that it returns a Boolean, even though it shouldn't be necessary. And our mint has an override. We haven't tested burn, have we? Well, we're most likely gonna have to do the same. Good. So we do have a burn. Is this working now? Should be. Yeah. Where do we have any burns? So CXX burn. Why is this working? Oh, it's working because we don't have any burns here, and we don't do the interface version. We use the actual one. So the last thing I want to do today is play a little bit with this. Instead of using test, we're going to use prove. And this will allow us to do symbolic execution. So I'm just going to copy this, and we're going to try to adapt it for our token, which should be simple enough. So how does this work? When you use prove instead of test, so this, when you call test, these are concrete executions. If you do a test with parameters, it's gonna use the fuzzer, so it's gonna try random values up to how many times you want it to do it. And if you call prove, it will actually do sort of formal verification. It will do symbolic execution. It will try to exhaust all possible ways that your code can run. And I mean, it's pretty freaking cool. So let's just copy this one from the examples. It says prove transfer, and let's see, because I've never used this before. It will send a supply, a user, and an amount, and this will all be symbolic, like I said. It says if the amount is greater than the supply, it returns. Okay, so yeah, we only want to test for things if the amount is under, you cannot send, it's gonna send a total supply, it's gonna mint a supply, okay? And the amount that we're gonna be working with should not be greater than the supply that we're gonna be working with. This is perfect. Then what does this do? It gets a balance from the user, a symbolic user. It transfers that amount to the user, and then it checks what the post balance of this transfer function is. And it does expected. If the user is the same as the address, then it's 0. Otherwise, it's the amount. Okay, this is good. So, because we have there are two different forks, right? One is if we're transferring from and to ourselves. So this is a no operation. Nothing changes. Otherwise, there's an amount that has changed, and we assert that the expected amount is the post balance minus the pre-balance. This is all good. Let's try this with our CXX token. And mint, how do we want to do this? Amount greater than supply. I think the easiest way is just to, let's burn the total supply. So we start at 0. And then we mint to ourselves whatever supply comes from this test. I have no idea what this is going to do. And this is taking a while. Oh, this is good. Prove transfer. It worked. So can we be pretty sure that our transfer function works? I hope so. Do we want to try it with the other token? This is the CXX2. 13 tests. Prove transfer 2. All of our tests, prove transfer. Wow. This is amazing. This is amazing. Let's see what else is here. Prove balance, prove supply. Wow. Let's grab all of these, at least for the first token. What does this do? We assert that a certain user has 0, then we mint some to the user, and then we assert that it has. Oh, this is good. And I want to try this because right now, this token, when it starts, the message sender has some balance. So this one should fail. And we want to see it fail, right? I hope we see it fail. Otherwise, we may be doing something wrong. Perfect. Prove balance. And let's see what happened. Prove balance. Counter example. Revert, call data, token test. Right, so if the user, this is the counter example. Token test is the address of our test contract, which is the one that did the deployment. So it's not 0, it's balance. It's however much the total supply was. So this is the perfect counterexample. And let's see what happens here. Prove balance, mint, or what's this? Maybe this is a different one. Token test. Oh, it actually found 3 counterexamples. Okay, so let's see. What if we do the same? What if we start everybody with 0? So we burn and if this doesn't work, then we have another no, there we go, prove balance. So this is the thing, we start everybody off with 0. Maybe I should just remove the initial mint from the constructor. And then let's see what this one does. So prove supply. So it just puts in a symbolic number for a supply. It mints that much, checks that the actual, this is even simpler, right? We just need to start with 0 supply. And then we mint to, this doesn't matter because it's not checking to whom. We can mint to ourselves, to somebody else. We just check that the actual supply is equal, which it should be. Like this, we're adding a nice amount of tests. I probably want to remove that token too. And I want to make just one. So likely it's not going to be this one. Yeah, I'm going to delete token 2, and token is going to be my main token because I like this one better. In fact, there are a few things that we can do. We don't need this anymore because balance of message sender should be this. Otherwise, if there's not enough, if this underflows, then it means we didn't have enough balance to start with. And transfer from, I want to be a little bit more careful here, but it should be the same. Like, we don't need this, right? We may have to do another video to make sure that we're doing the correct thing here, but it should be no, minus equal the amount. And this should also be minus equal the amount. Let's see, I don't know if we, right. We had to remove any mention of token 2. No more of this. And any test that had a token 2, we want to remove it. Probe transfer, I'm gonna remove transfer 2. So far, so good. Now, let's see what else is here. Probe add. Probe balance, probe supply, constructor arguments. These are all good. We should probe burn. What does this one do? The same, there no underflow. Hey, I found a bug. It's missing an R. Huh. If the amount is greater than the supply, it returns, fine. Then it mints the supply and it burns an amount. And it asserts that the supply minus what was minted minus what was burned equals the total supply. Perfect. Prove distributivity. Proof loop. Great. Can we, in the 10-15 minutes that we have left, do some kind of transfer from? Can we? Let's see. We burned the total supply, so we start with 0. This is the same. Whatever amount has to be greater than or equal to the... if it's greater to the supply, we return. So amount always has to be less than the total supply that we're going to be working with. And this one's going to be a little bit more complicated because we might need 2 users. And we're going to need... let's see. What do we need? We need 2 users. We need the prove. That's also... Let's see. We approve the user on that amount, right? Then instead of this, we do let's see, will this work? We want to create a new user. User u equals... Can we do this? Damn, if this works, it's going to be so good. And this user will want to do a transfer from the address this, which is the one that, come on. But for expected, oh right, the 4th one is CXX. Let's go over this again. And I don't know if this is going to work. Well, we may need to rewrite this. We start with 0 supply. We create a user, or we cast this user to an actual user that can call the functions that we want. We mint to ourselves the supply that we're going to be working with. We approve the user on whatever amount is given. And we check first that the balance of the user, we check whatever pre-balance is, we don't care. Then the user does a transfer from of this token from whoever did the minting to itself for an amount. Then it checks and expected, right. If we were ourselves, then nothing happened. Otherwise, the other user has. Oh man, I hope this freaking works. Failed. Let's see why. Not unique from buffer. Not unique from buffer, 32 bytes and this? Proof transfer from. What is this? This is transfer. I'm so fucking sad about this. What can we do? Approve. Is there anything that I'm doing wrong? Approve the user. Let's see. Transfer from to amount, from to amount. This is all really new to me and extremely powerful. But I don't know how to use it. What if we do it the other way around? Let's do it the other way around. And I want to save this for later. Copy. Let's do it the other way around. We start with nothing. We're not going to use this user. We're going to mint to the user however much supply. Oh, but then the user has to approve us. Ah, God damn it. This is what I want. From the user to me. Amount. And here, this I need, but it's not gonna. I want the user to do an approve. And the token from myself. But I'm probably gonna have the same mistake here. So I want to check the pre-balance of user. Yeah, we should actually be checking the address this, not the other one, but let's just see if I have any mistakes. Not unique from buffer. I have no idea. Okay, this is what I'm gonna do. I promise I'm gonna check for, gonna read the docs for approve. I'm gonna fix this, and next time we're gonna do as many of these proof functions as we can, get them passing, and then we're gonna try different implementations of ERC20s, and we're gonna run them against all of these proofs and see if they work. But for now, I think this is all. Happy Sunday, everybody.